All right, good evening once again, guys. Today we're going to be looking at some circle theorem. Just giving a little time for 1 hour or so more person to get in. All right, so circle theorem, as you know, has to do with the circle. And embedded in circle theorem, we also have tangent theorem. All right, so when we say circle theorem, we are really including tangent theorem as well. And we'll see what that is all about. All right. All right, so first we're going to start off by really defining the circle. A lot of what we're going to be looking at today will have to do with a lot of theories that you have to remember, because without understanding the theories or remembering the theories, you won't be able to apply them to the questions, and you need to know these before you can actually approach a lot of the questions in circle theorems, or in circles rather. So we have to get familiar with the definitions and so on. So starting out with the definition of the circle, a point A in a plane, and we know a plane is a flat surface. So a point A in a plane whose distance from a fixed point B in the plane is constant. So the distance from a point, one point to another point is constant, or should I say there's a fixed point. One point is fixed, but the other point has a constant distance that lies on the circumference of a circle. Anybody care to explain what they understand by circumference? Anybody know what circumference is?
Sir, the distance around a circle, sir.
Say that again, miss.
Sir, the distance around a circle.
The distance around the circle. In other words, it's the perimeter of the circle. All right. Now the fixed point at the center of the circle, we generally refer to it as a fixed, the center. Now the constant distance from the center, that when you move that line right around in a what we call a rotation or a revolution, that constant distance going to be the radius. And that radius, once it is moved around the circle, is going to be landing on the circumference right as it goes around. So the circumference is the perimeter of a circle, as I mentioned before. And this is what it looks like. So here at O, we would have the center. And then that line that goes from that center, give you the fixed distance, and the length of that distance is the radius. And once we keep that, if you imagine like the hand of a clock moving around in a circle, then that fixed point going to be on the circumference of the circle. All right, now we say radius is plural, and we say radii, radius is singular and radii is plural. All right. Now, we're going to be defining a chord. Now, a chord of a circle is a straight line joining 2 points on the circumference. All right. Now, one of the things that you must understand about a chord, the chord is when you find 1 point on the circumference, and then you draw that line that line from that point to another point on another part of the circumference. So that straight line is called a chord. Now, once you understand a chord, we know that the chord will divide the circle into two parts, right? Now, in terms of the circumference, it divides the circumference in two parts. Now, a part of the circumference forms kind of what we call an arc. So that section of the circumference, or a part of a circumference, is known as an arc. And that is ARC. So from here, going all the way around to here would be an arc. But the circle is, the circumference is cut into two arcs. And so the smaller arc is known as the minor arc, and the larger arc is known as the major arc. But the circle is also cut in two sections, right? And these sections, we refer to them as segments. Now, the circle then is cut into two segments by the arc, no, by the chord rather. Now, if you look at this, you realize that these two segments are of different sizes. And so the larger size, we refer to it as the major segment, and the smaller size is referred to as the minor segment, all right? So this arc, this chord would separate the segments, all right? And the chord also separates two arcs. All right, so that's a chord. Now a chord through the center of a circle is called the diameter of the circle. Now, we know that the radius also starts from the center of the circle. So if I ask you to relate the diameter and the circumference and the radius, if you are to relate the diameter and the radius, what can you say about the diameter and the radius in terms of some relationship?
The radius is half the diameter.
This is half the length of the diameter. So in other words, if you have the diameter and cut it into two equal parts, half the diameter would be the same as the length of the radius. All right. Now we talk about what we call concentric circles. Now concentric just simply means the center is the same for the two circles. If you know anything about abbreviations, we call it prefix in the English language. Prefix would be that part that you add to a word to give it to somewhat give it some clearer meaning. Like if you have the word right and you put the word re on it, you would get rewrite. So that prefix helps you to give a different meaning to the word right. So rewrite means to write again, whereas write means just write once or so on. So that re is the prefix. Now with the word concentric, centric means center, and the prefix con means width. So concentric, what it is really saying, with the same center. All right. So these two circles that we are looking at, there's an inner circle and there's an outer circle. one with radius capital R, one with radius common R. But they both have the same center. So the two circles are concentric because they are sharing the same center. All right, so concentric circles share the same center, but they're not necessarily having the same radius. All right, and if you're to find the area of the shaded region in blue, then this would be the formula. The area is equal to pi. As you know, area of a circle would be pi r squared. And so the area of the blue section would to be find the area of the inner circle, find the area of the outer circle, and then you subtract the area of the inner circle from the bigger circle, and then you will get the area of the blue section. But to just write that formula in a shorthand way, it is pi, the radius of the outer circle, minus the radius of the inner circle. All right, and so that will give you the shaded region in blue. All right, is that clear to everyone, guys? Raise your hand, let me see if you're following me. My voice is a little husky today. All right, I hope you're hearing me well. All right, good. Now, in different texts, circle theorem might be labeled in different texts as theorem 1. So even though this might appear in my notes as theorem 1, you might read another textbook where the theorem 1 may be a different rule for different rule in that theorem 1 from this one. And so theorem 1 really is based on whichever text you're using. All right, so in this notes, I'm going to refer to this as theorem 1. All right, so what theorem 1 says, a straight line drawn from the center of a circle to bisect a chord, which is not the diameter, is at right angle to the chord. And it is, if you think about when a chord is right angle to another, the radius is right angle to the chord, what it is saying is that the radius and the chord would be perpendicular to each other. All right, so perpendicular is just another big name to mean that two lines are at right angle to each other. All right, so the radius comes from the center down. It meets the chord at the center of the chord. So what they're saying is that once the radius is coming down vertical and the chord is going across, it will cut this chord into two equal parts, and it will be at right angle to the chord. All right, any question? All right, no question. Now, theorem 2, somewhat looking like theorem 1, but they are very different. So a straight line drawn from the center of the circle and is at right angle to a chord, which is not the diameter, bisects the chord. That means it's cut into two equal parts. So if we go back to theorem 1, theorem 1 is just saying that the radius is at right angle to the chord. But theorem 2 is saying that the radius bisects the chord, meaning it cuts the chord into two equal parts. So one is saying that, so one part of the theorem is saying that they are at right angle. The other part is saying that you're bisecting the chord. And bisecting a line or a chord means that you cut the line in two equal parts. All right. Now, chords of a circle with equal length. So chords of a circle with equal length. So this chord AB, the chord from this part of the circumference to B. So this chord AB have the same length as the chord CD. Now, because these chords have equal lengths, the theorem is saying that chords of a circle with equal lengths are the same distance from the center. So this chord, so if you draw another chord somewhere around here, if you draw another chord from this point to say this point, and once this chord is the same length as the other chords, the distance from the center will be the same as the others. Is that clear, guys? Raise your hand if it is clear what I'm explaining to you. So if this length, the length of the chord is the same length as the other chords, it means that that line from the center to that chord will be the same as the length of that line to the other chord. So all of these lengths would be the same from the center because all of the lengths of these chords are the same. That's all it is saying. All right. Now, Theorem 4 says that chords which are equal, all right, are equidistant from the center, meaning that they are equal length from the center of a circle. The lengths are equal in length. So as before, this is saying now if the distance from the center are the same, then, so what this is really saying in terms of the theorem is that they're given a vice versa thing where the theorem is saying. Now the first theorem had said, if these chords CD and AB, if they have equal length, then they are the same distance from the center. Now they are saying, if these chords from the center, if these radius, well, not radius, but if these lines from the center to the chord, if these lines are equal length, then the chord that they are perpendicular to would be equal length. So it is actually doing a vice versa thing with the theorem 3. So theorem 3 and theorem 4 is pretty much the same theorem, but they are just saying it in a vice versa way. So theorem 3 would say if A, B, and AC are of equal length, then the distance to the center must be equal. This theorem is saying if the distance from the center is equal, then the chords that they are perpendicular to must be equal in length. So that's all this is saying. Moving along. Here now, a chord which is not the diameter divides the circumference of a circle into two arcs. Now, remember now, the arc is just a part of the circumference. And so this pink line going all the way from where the chord is on the circumference. So from that point of the chord, going around to the other point of the chord, this pink part of the circumference is an arc because it's a section of the circumference. And if you're comparing with the other section of the circumference, which is the blue section, you will see that the pink section is shorter than the blue section, the blue arc. Which one of them is longer? The blue arc is longer than the pink arc. And so the pink arc, being the shorter one, is referred to as the minor arc. And the blue arc is referred to as the major arc. All right, so we say that a chord which is not the diameter divides the circumference of a circle into two arcs, minor arc and major arc. Now here we have the largest section of the circumference is called the major arc. And the smaller section is called the minor arc. Now here we are talking about the segments. I would have mentioned these before. So a chord which is not the center divides the circle into two segments. The region in the pink region is the minor segment, and the region in the blue part of the circumference is the major segment. The larger region of the circle is called the major segment. The smaller region of the circle is called the minor segment. All right, theorem 7 here says, angle subtends at any point on an arc is in the same segment by a chord AB, or 2 points AB on the circumference are equal. All right, so all that is saying, if, give me a second, guys. All right, guys, so all this is saying, they're saying that if you have an arc AB, sorry, not an arc, but a chord AB, and from the point A and the point B, you form an angle in the major segment. Now, the bigger portion of the circle where these angles are formed is the major segment. So if you form an angle, we use a different color. If you form an angle starting from the point A, you form an angle at the circumference from A to B, right? So this angle that you form here, now if you also from the same A, form another angle in the same segment. All this is saying is that angles that are formed in the same segment are equal. So this angle is X, this angle is X, because they are formed in the same segment. Now, to give a little bit more clarity to what I'm saying, suppose instead I form an angle now from A, and I form an angle here. And I form from A to B. and I start again from A, from an angle A, from A, I form an angle from A to B again. Now, which segment these two angles are from? Major or minor? Anybody? Guys?
Sir, minor.
Can you speak a little louder, Dorothy? I'm not hearing you at all.
Sir, I'm saying if it's minor because since this...
Is it that your mic is not working, Dorothy? I'm really hardly hearing you.
Sir, hearing me now?
You're very low, very low. Turn up your mic or something. You were loud earlier on. So if you use
the rain is
you're using an earpiece.
No, sir, but the rain.
You need to plug out the earpiece. It's generally lower when you use the earpiece. All right. So anybody else can tell me what segment is this angle formed in? The angle Y, major or minor?
Comparing to which one, sir?
I'm saying there are two segments here, major and minor segment. How do you distinguish which segment is major, which segment is minor?
All right, sir. Where the two? Where you're referring to the two y angles, sir?
Well, apparently you guys weren't paying attention when I was defining what segment of a circle is. Can anybody remind me what the segment of a circle is?
The segment would be the large, sir, where the card cuts the circle. So you have the bigger one, you have the smaller one, but I'm confused because I'm seeing a whole lot of lines here. So I'm not sure if you're talking from where the dotted line is, or are you referring to the two brown one where I see Y is at?
All right, so in the question, if you pay attention to the question, which one of the cards form the center, the segment?
The one A to AB, sir.
Right. So if AB form the segment, which part of the circle would be the segment?
The part we have YY, sir, and the next part we have XX.
Remember,
just not that theorem yet.
You start from A, following this circumference, going back.
Yes, sir.
You're going above and going all the way back around to B.
Yes, sir.
That section of the circle is divided by the line AB from this section of the circle, which is down below.
Yes, sir.
So the one above is that section and one below is the other section. So both of these sections are segments.
Yes, sir.
So which of them is the smaller segment and which is the larger one? The one above?
The larger one is above, sir, and the smaller one is below.
Okay, good. Now looking back now at where the angles are formed for X, which segment would that be in? Larger or smaller?
Larger, sir.
The one that I drew for Y, which segment those angles are in?
Smaller segment, sir.
Smaller segment. What you notice about the angles above? Which segment the angles above are in?
Sir, remember that we want anything equal to what it might be same. Remember what you call it, sir. Same answer. So if you calculate one angle, you don't automatically find.
Answer, Miss Wilson, asking which segment the angles are formed in.
Segment. Sir, the larger segment.
The larger segment. So both of these angles are in the large segment. Down below, both of the Y angles are in the
smaller segment.
Right. Now the theorem is saying that angles that are formed in the same segment are the same. That's why they're equal.
Mm-hmm.
Right. So it means then the angles that are formed in the segment above